All right. Everybody good? How are we doing for time? Have what? Half an hour? 25 minutes. Excellent. Are people following this? I've been manic this term, and we're just flying through this material, partly because nobody interrupts me but him, and I don't really listen to him. Yes, what? Uh-huh. Right? I don't know what that O1's doing there. Oh, we're going on to other things that we didn't do. Amortized time. All right? We did an amortized time already, right? Remember when I pushed those buildings and then I might pop a lot of them, but no building gets popped more than once, right? That was called amortized time, right? And we're going to look at another example of amortized time, all right? So suppose we're filling up an array, right? Maybe this is our queue or our stack, and we're implementing it not by a linked list, which you can keep growing, but we're implementing it by an array, right? Why? Because you don't have to deal with all those pointers, right? So when it gets full, what do? Well, we gotta get a bigger array and copy it over, right? And start over. Everybody agree with that? How large, when we go from something of size, say, n, how much bigger should we make it, right? Should we go from n to n plus c? Should we give us a constant times more things, right? Or maybe we should double our size. If it was this big, double it, right? Does that make sense? I got an array this big. I got to copy everybody down. That was a lot of work. How much bigger should I make the thing, right? I could make it another c bigger, or I could double its size, right? Everybody buy that? Anybody want to vote? Which one looks better? What? Plus c. He's voting for plus c. Anybody want to vote for plus c? Anybody want to vote for doubling? All right, let's see who wins. All right. All right, so what we want to, the person on the outside using this program doesn't know about your implementation, right? And it could be that he does an add of an item and you had to increase the array and it took a long time, but he doesn't mind so much as long as the average time I do an insertion doesn't take too much time, right? Do I get that? So some insertions might be really expensive, like this one, right? But we want to calculate the average insertion time, all right? Everybody get that? So what's the average? Is if I do n insertions, I have a data structure, I have an abstract data structure like a queue, and I do n pushes and pops, right? In any order I want, I can push, 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 pop, 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 or just push, right? I do n of them. I take the total time. I divide by the number of operations I do. That gives me the average time per operation, right? And what do we want our average time to be? Constant. We want our average time to be constant. Why? Because in our linked list it was constant, right? And we want a constant, right? All right. So let's see. If we add an element to the end, it just takes a constant time. That's no problem, right? So if we do that n times, the time is n, and the average is 1. Right? Everybody agree? That was easy. All right. Now it's allocating the new memory that kills us. Right? So let's say that to allocate an array of size k takes k time. Right? Partly because you're copying things. Right? All right. So if I do this strategy, I go from n to n plus c. Right? Then when do I have to do it, right? I start off with the small array, the zero, a zero array. Maybe I start off with one of size c, right? And then it gets full, so I go to 2c. And then it gets full, so I go to 3c, right? And I keep going until I've done all of them. Right? Everybody see our time? What's happening? We have to, every c insertions, addings, we have to do an update, right? Well, what's the total time? Well, this update cost me c, and this update cost me 2c, right? Everybody see that? The last one, I was getting an array of size n, it cost me n. So the total, right? We're doing 1 plus 2 plus 3 up to n over c, right? You add this all up, and it gets to, well, we got a c here, and we got n over c squared, right? You bring the c's around, and there we got it, right? Here the c's on the bottom. It's not a 2 to the c, it's divided by 2c, right? Everybody good? All right. How many operations we do? We did any operations. So what's the amortized time? Order n, right? Everybody got that? Order n, that was bad. Right, everybody right? Okay, so anybody who voted add C, it was bad. All right, let's do it again, but we're gonna double, all right? All right, so my array is at first of size 1, and then it's 2 full, so 2, 4, 8, it doubles, right? Everybody see it doubles until I get to n. That's when I need to allocate space, right? How much does that cost? That costs the sum of this. Anybody know what this sum adds up to? You did it in 1019 probably, right? Here, look at, I got 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64. What's the sum? It's 2 times the biggest number minus 1, right? The terms are growing so fast that it's dominated. The sum is dominated by that last term, right? So it's dominated by the n, right? So the time is order n. The sum time is order n. We amortize it, and we get a constant, right? Does that make sense? So the intuition is doubling it, right? In fact, I kind of lied to you a little bit here. Yeah? Amortized? It means the average per. I'm spreading the cost over, I don't know if you looked that up in the dictionary what English would mean. Anybody heard the English definition of amortized? Well, anyway, I have a number of operations. It could be this operation was really expensive, but amortized over all my, averaged over all my operations, we're good, right? Now, what I didn't say here is suppose my input's this big, and I get a little bit more, and I double it, and I didn't need to double it, right? I was done, really. That cost me an extra 2n work, right? That was bad. Oh, yeah, but do I really care? 2n divided by 2n, amortized is only an extra 2, right? People see that? And that is the joy of amortized. And then we did this example, right? Everybody good? Yeah. All right. So here's the bottom line. If you think about constants, right? If every constant time I get a new a number added, right? Let's say my constant's 10. Every 10, I have to reallocate space, right? So how often do I have to reallocate space? Order in time, n over 10, right? I have to reallocate space, order in time. How much is it going to cost me each time I reallocate space? Well, most of those times, my time is about n. My thing is about n. So most of those times, it's going to take me order in time to copy the list down, right? So if I reallocate the space, order in time, and each one takes me order in time, then the time to do these inner operations is order n squared, right? I'm in the middle of something, right? Does that make sense? So that's what we're saying here, right? We don't care about these constants, but they're order in, these are our order in times that we have to reallocate, and each one takes me order in time, right? So the total time is n squared. And then I divide by the number of operations, and that's order n per time, right? Now, if we go over here, if I double every time, right? Start with 1, and I double it, and I double it, and I double it. How many times do I have to double? Log n times, right? Log n is small, right? So I only have to reallocate space every log n time, right? That's the difference. Before we were allocating space order n time, and now we're only doing it order log n time, right? Now, let's say I still charge you n for reallocating, right? Then the total running time is n log n, right? Log n reallocations, right? N time per, that's n log n time, right? So then we divide by n because I'm amortizing, right? And what do I get? I get log n time per operation, right? Does that make sense? And log n is way better than n, right? Yeah, but it's better than that, right? It's better than that. Why? Because here my biggest term is 64, but the sum is not 64 times the times the log n times the. It's not 64 times the number of squares, is it? It's only 2 times the biggest number, right? So this sum here, right? If you charge me 1, then you charge me 2, and then you charge me 4, and then you charge me 8, the total you're going to charge me is twice the biggest number, right? So my total charge is order, right? Even if you make me double it again, right? I get charged twice as much as I should have, right? Then the sum is 4n, right? Yeah, but 4n's not so bad because we divide by n and we get a constant 4, right? Does that make sense? Everybody good with that? Okay, we did this example. All right. Everybody good? Now what are we doing? We're doing another 10 minutes? 5 minutes? 10 minutes? All right. So we want to talk about which there are 2 to the n inputs of size n, right? N bits. And when we talk about the running time, we talk about the running time of inputs of size n, right? So which input do we choose? We could talk about a random input of size n. We talk about the input that gives you the smallest runtime. We could give you the input that has the biggest runtime, right? Which one of those do you think we go for? Nope. Right? For example, if I give you n numbers to sort and they're all 0, then I can sort it really fast. Yeah, right? So here you could say typical input, but I don't know what that means, right? What is typical to who? We could say average, but what distribution, right? We could say worst case. And that's what we're going to do. We're going to bound it by the worst case. All right? Everybody good? Now, I don't know if this is useful or not, but if I want to know who the tallest person in the class is, right? Right? If I want to know whether the tallest person is bigger than this, I only need to find one person who's taller, right? But to kind of prove that the tallest person is shorter than this, I got to look at everybody. I don't know. Time complexity is going to be hard to find, right? When I talk about formal time complexity, is you measure the size of the input in bits. And oh, here, there's a difference between the time complexity of an algorithm, right, versus the time complexity of a problem, right? So right now we're talking about the time. I give you a piece of code, and I want to know the time complexity of it, right? I have to prove, if I want to prove it's big O of n squared, then I have to prove that every input takes less than some constant times n squared. You give me an arbitrary input, and it's got to take time less than this, right? This says I want to prove the opposite. I want to prove that there is at least one input that takes that much time, right? And this one says you do both. Remember, you guys learned big O and omega and theta, right? This one usually we say your running time is order n squared. Why? Because it says that every input would take at most n squared time. To do theta, you have to say we know that they're a worst case, right? You can't do better. All right. So now we want to so this wasn't so bad, right? You can find an input that takes this much time, right? Now, what about time complexity of a problem, like sorting, right? To prove that you can sort in n squared time, you have to give me an algorithm that can sort in n squared time. Selection sort, right? To prove that the complexity of sorting is omega n squared, you have to prove to me that you can't sort faster. And that's now impossible. Why? Because you can't sort faster. You can sort faster, right? But it could be a different problem, right? Let's say multiplying. I can show you that I can multiply in n squared time, but can I multiply faster? You think you might not be able to, but the truth is you can multiply in n log n time. How? You use fast Fourier transforms. Are we going to cover that in this course? Absolutely not. Right? I would love to. It's a beautiful algorithm, but we're not going to cover it. All right? I don't even cover it in 3101. I cover it when I do the grad class. All right? All right, everybody sort of follow that? And that's when you talk about the time complexity of a problem, we tend to use big O because we don't know whether it can be done faster, right? And I think we're probably out of time now. Everybody good? Any questions? 4 minutes? No? Next, we're going to talk, we did this about classifying functions already, and we might not even do it again. I don't know. Do people need to do this again? Adding made easy. I don't know. I just threw various things in here. Let's think about what we're going to do next class. What else we got in these slides? Worst case, classifying functions, adding logs and exponentials, understanding quantifiers. Probably no. I don't know how many of those are also part of the course. I should talk to Jackie because I don't want to cover a lot more than he covers. Any other thoughts? Everybody good? All right. Today is Monday. Have a good Tuesday. Have a good Monday night.